That should work. Hello, everybody out there in podcast land. This is part B. We stopped somewhere around KB, so I'm going to look for the last one that we did. We wrote KB expressions. I think 23 is one we did not do. So we will go ahead and start with 23. Had to set the mood lighting a little bit for everybody. Calcium hydroxide is dissolved in water until the pH of the solution is 10.84. The hydroxide ion concentration of the solution is, hydroxide ion concentration is, so the first thing you want to do to find hydroxide ion concentration, you get that from POH. But this is pH. I can get POH because it equals 14 minus pH. People are talking over there. Don't you know when I'm podcasting you can do things that I wouldn't notice, like, I don't know, text or call someone where I can't hear, but that's way too loud. So 14 minus pH, so 14 minus 10.84 would be 3.16. And that is the POH. To get your OH concentration, that is 10 to the negative POH. If you're not comfortable with these equations yet, become comfortable with them. I don't know what you have to do to memorize them. They're on your equation sheet. They were on an earlier podcast where you just kind of chant them to yourselves or whatever it is that you do. So get out your calculator, and 10 to the negative 3.16, second log negative 3.16, is 6.92 e negative 4. Good. The other thing you can do is, if you see this is about 11, you could see the POH is about 3. So you can narrow choices down to be something around 10 to the negative 3rd or 10 to the negative 4th. So that's an estimation thing you should be able to do. Ka for HCN is 6.2 E negative 3. What is the Kb for Cn negative? This is important. This is to find the pH of salts. It's number 77, of course. Kas and Kbs are related. Is Cn negative a base? Yes, because it is a hydrogen acceptor. H positive loves the negative on Cn negative. So what happens is you can see Cn negative reacting with water to form HCN plus OH negative. So you get all this junk, and this is nice to kind of introduce you to it, but really all you need to know is Ka times Kb equals Kw. Kw is 1 e to the negative 14. And what Kw is, it's the autoionization of water. So H2O plus H2O is in equilibrium with H3O positive plus OH negative. Now, if I were to write the K of this expression, because these are waters and I don't worry about them because they're liquids, it would be simply H3O positive times OH negative. And the best and brightest of you out there in podcast land do know that the pH of pure water is 7. So if the pH of pure water is 7, then H positive equals 10 to the negative 7th. Oh, what would the POH of water be? 7. So if POH is 7, that means OH negative concentration is 10 to the negative 7. 10 to the negative 7 times 10 to the negative 7 is 10 to the negative 14. Because solutions are in water, Ka times Kb equals Kw. That water is kind of a constraining factor unless our molarities get very large. So if my Ka is 6.23 e negative 10 times Kb equals 1 e negative 14, we then know what to do, although what I wrote was completely illegible. 1 e negative 14 divided by 6.23 e negative 10, and I get 1.605. Oh, that's it, e negative 5. What is the pH of 0.75 molar solution of sodium fluoride if the Ka of HF is 7.2 E negative 4? Sodium fluoride is NaF, and you wouldn't expect that. That's not an acid nor a base. It is a salt. Salts are made of acid parts and base parts. This is the part from a base. This is the part from an acid. This comes from a strong base. Strong bases, remember, ionize 100%. That means Na positive will not attract OH negatives. Why? Strong base. Ionize 100%. Definition. Will Na positive like H positives? Will a positive like a positive? No, that's just silly. So that means all I'm worried about is my F negative. Oh, by the way, sodium, so all I have to worry about is fluoride. So F negative plus H2O will give me HF plus OH negative. Here's the Ka of HF, but what do I want to deal with here? It's not acting as an acid. I'm using its conjugate base. So 7.2 E negative 4 times Kb equals 1 E negative 14. And again, that's my Kw expression. So 1 E negative 14 divided by 7.2 E negative 4 is 1.39 E negative 11. And that is, so the pH, well, now I know the Kb of it. So now I have to do the, is my molarity going to be 0.79 if this breaks up NaF? Yes. Why do you ask that stupid question? What if it was calcium fluoride? Calcium would be a strong base, no effect on pH. But fluoride would be F2, so rather than having a concentration of 0.75 for my initial, it would be 1.5. So watch your dissolving equations or whatever it is here. But this is 0.75. Nothing, nothing. Minus x plus x plus x. 0.75 minus x, x, x. Solver time. 1.39 E negative 11 equals x squared over 0.75 minus x. And I get that bad boy out. Whoops. If I could hit the right button. And I got x equals 3.3 E negative 6. That doesn't look like a 3. So what is the pH of it? So that's x, and that equals hydroxide ion concentration. So from that hydroxide ion concentration, I can negative log that bad boy. And that would give me POH, negative log. That answer is 5.49. And then pH equals, yes, you have to show this, 14 minus 5.49. And that noise is Paul Scheid, blowing his nose. Pause. Okay, important point here. If you happen to get something that's a negative number, you'll never have a negative value for x. So you would want to change your bounds on that case. I assume that the bounds automatically revert to negative 1 E99 to positive 1 E99. So whenever you get something that's silly, just change your bounds to make it unsilly. So this would be 8.51 would be pH. Okay, this slide looks short. Multiple OHs are strong. Find the pH of 0.025 molar barium hydroxide. Why don't I give you a Kb here? Why is there no Kb? You don't need it. That's true. Why don't I need a Kb? What type of substance is barium hydroxide? It is a strong base. Remember, the strong bases are group 1 and group 2 hydroxides. Your strong acids, which I haven't listed in this acid chapter again, but it's HCl, HBr, HI, HNO3, H2SO4, and HClO4. Remember, HF is weak. Most of the other halogens are strong, but HF is weak. Which kind of goes against the polarity thing. The reason why that polarity thing is broken, remember I said the more polar the bond, that's where it's going to separate. This is because the sizes are so small, it's hard to disrupt that. So if this is strong, I don't need a Kb. What's the hydroxide ion concentration here? I'll give you a hint, not 0.025. 0.05. Why? 2 hydroxides would give me double the concentration of it. So that would mean negative log, wow, that's weird, negative log 0.05 would equal POH. So that's 1.03, which makes sense, a low POH for something that's very basic. And then pH would be 14 minus 1.03, which would be 12.97. Yay. Ranking acid-base strength. Strong acids have weak conjugate bases. I'm going to even put in parentheses, they have no conjugate bases. Because strong acids ionize 100%, if HCl ionizes 100% to make H positive plus Cl negative, I suppose I should put water in there. That means Cl negative will never react with water. Cl negative will never react with water, or H3O positive even. That equals nothing. By the definition of a strong base, HCl together as a unit does not exist. It ionizes 100%. Weak acids have powerful conjugate bases. We talked about how you can have 99% ionization and be weak, but in reality, weak acids are virtually always less than 5%, and most of the time less than 1%. That means if I put it in solution, 99% of it is HA together. 99% of it is HA together. Only 1% of it will ionize. And that's an acid? If something happens 1% of the time, you tend to ignore it. All right? So that's very, very odd that it's so substantial. But 1% of whatever it is, compared to nothing is substantial. Strong bases have weak conjugate acids. And remember, I'm going to put here, I'm going to make it no conjugate acids, because they will not react in the reverse way at all. Weak bases have powerful conjugate bases. Again, I really prefer the word powerful because they're very powerful, but they're not quite strong. Okay, and a little bit of a difference between those. All right, get your sheet out. Number 6, which we already did. Using K, values indicate the order of base strength. So I'm looking at the conjugates here. So this is the best acid. This is the middle. And this is the worst. So the worst acid would have the best conjugate base. And the best acid would have the worst conjugate base. And then the middle acid is in the middle. Okay. So you'd think there'd only be 3 choices, but of course they're torturing us with even more. Cl negative comes from what kind of acid? Strong. So what kind of base is it? It's terrible. So that would be the worst. I'm agreeing with that. Cl negative is the worst. So then I'm going to look at this one to see if this would make sense. Ooh. So I've got my 2 with Cl negative on the bottom. So I've got Cn negative. I could actually calculate its Kb, couldn't I? And its Kb would be, if that's 10 to the negative 4th, K times Kb is Kw. So welcome back to 2nd grade. 7 is bigger than 4. That means HF is the best acid. And HNO2 is the middle. So that means this would be the best conjugate base, this would be the worst conjugate base, and this would be left over. Okay, so chloride's still going to be the worst. I'm going to start assuming that those would work in that method. So this would be the best conjugate base because it's from the worst one, so I like that. So water, don't like that. So let's see here. We've got water, so we've got Cn negative, then we've got NO2 negative, then we have F negative, then we have H2O. Okay, so what do you think is going to be better, F negative or H2O? And that's what we're going to look at first. Now, F negative is a powerful conjugate base, but still it's a base, right? It's a powerful base. When I say water, do you go, ooh, powerful base? No, you go, it's water. Is that even a base? Yes, of course it can be, but it's not powerful. So I'm going with A, and I'm a happy camper. Okay? Because it fits our rankings up here. By the way, the best base in the whole wide world is OH negative. That's the best one in the whole wide world. You should know that. The worst base in the whole wide world would be H positive, which kind of makes some sense. Equilibrium constant for blah, 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 blah. Relative order of base strength is, these are the exact same ones, aren't they? Oh, except for water. Yeah, so we know that this is the stronger acid. This is the weaker acid. So we know that CN negative is the better conjugate base. So this is the best conjugate base. This is worse, but still powerful. So we should see CN negative, F negative, water. Conjugate base of a weak acid is a, is it strong? It's powerful. I'm going with E. It is not strong. It is not strong. It's powerful. Well, it's not that either. The real answer is none of these. That would never be a multiple choice question. The real answer is powerful. You won't see the word powerful, but strong, acid, and base has a definite connotation. It means perfect 100% ionization. Really, it's almost 100%. But that's not going to be strong. So that's important to know. If I said, what's a stronger base? F negative or NaOH? What's your stronger base? It's got to be NaOH, because NaOH really essentially equals OH negative, which is the Lil Wayne of bases. Right? All those electrons to give away. Right? Review. I forgot everything that we did, so let's just be done with it and be glad we could split this into two parts. So review the lots.